forcing functions. Am I audible? Am I audible?
Yes, sir, audible.
Okay. So in the last lecture, we identified that once we derived the expression of transfer function, now next step is to develop a function, that is the response should be in the form of time. Okay. So likewise, so, so ys by xs was the expression 1 upon 1 plus tau s. So ys is equal to xs into 1 upon 1 plus tau s. And this xs nature of xs, that is the input, is based on the what type of input we are deliberately introducing into the system. We are just doing it by deliberately we are performing this task to identify the response of the system. So that response of the system are depend upon what type of the types of input changes. The input changes. Input changes can be modeled in the mathematical format, and there are four types. One is step forcing function. Next is impulse forcing function. Third is ramp or linear forcing function. And fourth one is sinusoidal forcing function. So we had started uh, step forcing function. As this particular equation represent that before t is equal to 0, deviation was 0. So we considering that the x is any variable. It may be a temperature, pressure, flow rate, concentration. So it observed that this is a deviation variable. Deviation variable is 0 before the disturbance has entered into the system. Okay, so it was at 0 value. So deviation was 0. Suddenly, the of magnitude A, the change occurred, and that change will remain as it is. Okay, it may be because of the a sudden opening of the wall. Okay, so the flow rate will be constant, or the temperature we are setting, then it will remain constant. Okay, from different value. So as soon as at time t is equal to 0, it entered, that is the change entered into the system. Okay, the x is in the transfer function is the input. The input is changing in this fashion. Okay, sudden increase by the magnitude a, increase or decrease. Okay, or the sudden change by the magnitude of a. So it's this is xt is a into ut. Ut is the unit function of multiplied by the magnitude by which it is changing. So Laplace is a by s. So what was our concept? What was our concept? Our concept was our concept was so is this visible?
Yes, sir.
So so ultimately ys by xs is equal to 1 upon 1 plus tau s was the equation. So since there is a step change occurred, step change in input. What is the input? Input is my xt. Okay, xt of magnitude a. So it becomes ys is equal to so its Laplace will be xs is equal to 1 by s. So ultimately we can rewrite xs is 1 a by s into 1 plus tau s. So this is the expression we had derived yesterday. Similarly, to convert it into the yt, my aim is now is to convert it into the yt. Okay, so I use partial fraction. So I observe that and taking inverse Laplace and inverse Laplace transform. So I got yt is equal to a 1 minus e raised to power minus t by tau. This was my final expression. Okay, this was my final expression. यहाँ तक हम आ गए थे. Okay, now aim is sketch the nature of yt with respect to time. For that purpose, in this expression, I will put value of time and then I will calculate yt 0 to 100. So whatever the yt we get. So you just give me the nature of what yt profile you will get out of this in general. Okay, so before the moon increasing, correct? Increasing, but see, let me tell you, my xt profile was like this. Like, how the yt will be. Will be the same of the same shape? Will it be of the same shape? Hmm? Yes, correct. So what nature you are expecting? You just plot it, and you will observe that. So take it was the example. Example was the thermometer. Again, I am narrating the same thing. A thermometer having a time constant of 10 seconds. Time constant was 10 seconds. Okay. Is placed in the temperature bath. After thermometer reaches steady state temperature of 30, there were two temperature bath. One was at 30 degrees centigrade and one was at 60 डिग्री सेंटीग्रेड. ठीक है, थर्मामीटर पहले मैंने प्लेस किया है यहाँ. Okay, this is a thermometer. I'm just representing by the vertical line. After the thermometer reaches steady state temperature of 30 degrees centigrade, it is suddenly placed in a hot fluid at 60 degrees centigrade. And suddenly I'm immersing it into the 60 by removing it from these to this. Okay, so initially the temperature indicated by the mercury in the thermometer itself and the temperature of the liquid was 30. So we call it as a steady state. We call it as a, so at that time Ys was xs is equal to 30. But suddenly I am immersing that thermometer remaining from the 30-degree path into the 60-degree path. So this is the what we call the magnitude of change. Okay, so suddenly placed into the hot fluid of 60. Sketch the response of the thermometer. तो आपको क्या करना है? I have an equation. Okay, I have the equation. I have the equation. Yt is equal to a 1 minus e to the power minus t by tau. मुझे क्या करना है? Yt प्लॉट करना है with respect to time. The time is a variable. Tau is known. Tau is 10 seconds. And A is, what is A? What is A? A is this magnitude. This is the A. It is ये 60 है और ये 30 है initial. So 60 minus 30 will be 30 of magnitude 30. Is this okay? So plot the graph. You will observe that it will reach like this. YT will move in this fashion. YT will move in this fashion. Agree? You can plot it. It will move in this fashion. देखिए, you try that in Excel. Okay. Now some characteristics of this particular nature. This particular nature we will discuss here. We'll discuss here. Uh, we will discuss here little bit. Another example of the same thing, first order system and input changes of step change. So it is a mixing process. Okay, mixing process. So you will get the same. This is a homework for you. कि mixing process के लिए you develop a transfer function and implement the step response over there. The step change of input in input variable x is equal to a. This is visible. Step response. So step response, we have derived the things. So some outcomes or the characteristics of this step response will be discussed now. YT reaches 63.2% of its ultimate value when the time elapsed is equal to one time constant tau. This is the property of response when the first order system is experiencing, and that's response is of change of step change. Input change is step change. It represents that the ultimate change 0 to 1. Okay, see here, वो magnitude हमने अगर 0 to 1 में divide कर दिया है, what was the magnitude? 25 to 30. Okay, divide into the 100 parts or the 10 parts. So 0 to 1 में अगर मैं उसको define करता हूँ, that magnitude is of 10 units. I will divide it into the 10 equal parts. So I can place it into the small scale. Okay, whatever be the scale, if I am dividing into the 10, then it will be in this format. समझ में आ रहा है? हम स्केल डाउन कर रहे हैं उसको या फिर स्केल अप भी कर सकते हैं, नॉट एन इशू. बट इफ आई एम टारगेटिंग दैट परसेंटेज चेंज इज माय 100%, जो भी मैंने चेंज दिया है आई एम कंसीडरिंग इट एज अ 100%, देन इट रिप्रेजेंट दैट the system is first order and the change is for step change, then the response or the output reaches its 63.2%. See this point, 63.2% in first time constant. This is a time constant. When small t by tau is equal to 1, that means the time is equal to time constant. It may be a 10 second, it may be a 30 second, it may be a 1 second or any. So this particular graph represents that in one time constant, if your system is first order, if the input change is step change, then the response yt will reach its 63.2% of its ultimate change is from 0 to 1. In, okay, it is 63.2% at when time is one time constant. Is this okay? Are you getting my point? Any question? Students, this is just a property, okay? And you can implement it at any value, at any change, at any magnitude. So हम इसको rounded off कर रहे हैं बस. whatever the change of any magnitude, we are considering it is 100%. So to reach that particular 100%, it will take some time. So it represents that कि 63.2% वो achieve कर है ना 50% achieve करना है. So likewise 63.2% change it will reach in first time constant when time is elapsed as one time constant. Is this okay? Any question? Okay. So when the time elapsed is 2 tau, 3 tau, and 4 tau, the percent response is 86.5, 95, and 98% respectively. From these facts, one can consider the response essentially completed in 3 to 4 time constant. Okay, this is a general observation. Second is the slope of the response curve at the origin in figure this figure is mean that if the initial rate of the change of yt were maintained, the response would be complete in one time constant. Agar the response which is experiencing at time t is equal to 0, if the system or the yt follow the same speed, then there is a possibility that it will reach the ultimate change in one time constant. This dotted line represents the same. अगर response को follow करता है तो it will move in this way, but it is not following that path. It is following this path. Okay, this is the general observation and the characteristics of uh, any system which is influenced under the step change in the input. Okay, experience in the input change, input step change. Is this okay? Okay, now we will move on. The next one is impulse forcing function. Okay, so we are not going into the derivation of these things. So xt is equal to a del t. Okay, unit impulse function, it is represented in this fashion. Okay, and impulse function, as I explained earlier, that it is just like the tank is there, constant output equal to constant output. So there is no accumulation at all, will be zero. There is a accumulation, but it will not change with respect to time h. But suddenly a bucket full of water I am adding into the tank, what will happen? The height h will increase slowly. Okay, and then it will decrease. Okay, so the Laplace of, that is the x of s, xs is equal to only the magnitude by which it is changing will be xs. Okay, this is the property of actually the Laplace. The impulse forcing functions, its Laplace is the magnitude of that change only. That magnitude of that change only. Okay, unit step change में क्या था? It was a by s. Now in this impulse forcing function, it is only a. It is only a. Okay, agree? देखिए यहाँ अप्रोक्सीमेशन किया जाता है, ये रेक्टेंगल बॉक्स दिख रहा है, but it is not the case. Actually, it is just like peak. Okay, suddenly it will reach at height h, and at the same time it will start going down. It will start decreasing. Okay, it will not stay there for some time. Generally 0 to b, that thickness is very, very small. It is negligible. It is just like peak only. Okay, so the ultimate aim is, what is the nature of xs? So xs will be of magnitude of that change only. Agree? So take an example of that. Is this visible? Is this visible? Okay, the question is, a first order system is subjected to the impulse forcing function of magnitude 5. Of magnitude 5. So a is equal to 5. A is equal to 5. The time constant of the system is 6 seconds. Tau is equal to 6 seconds. Sketch the response for the system. Sketch the response for the system. Now see, I have Gs is equal to Ys by Xs is equal to 1 upon 1 plus 2s since it is first order. Okay. So xt is equal to A. That's the impulse change. So it is Xs itself of magnitude of A. We have already discussed in the previous slide. So Xs value I will substituting over here in the equation number 1. So Ys is equal to A by 1 plus tau h. Now further to resolve it, A by tau h plus 1 upon tau. Taking inverse Laplace on both sides, inverse Laplace of Ys is nothing but Yt. Inverse Laplace of this is A by tau into e raised to power minus t by tau. Now again, how to plot it? I have A is equal to 5. I have tau is equal to 6 seconds. Yt is equal to 5 by 6 e raised to power minus t by tau. Change the value of 1, 2, 3 and calculate y. Calculate yt in this fashion. So it will be like this. Yes, yeah. To get time t is equal to 0, it will reach at height h something. है ना? थोड़ा ये आएगा. ऐसे आता है वो कर्व. देखिए प्लॉट करके. So it is different than that of the our step change. है ना? नेचर अलग है. इसका नेचर अलग है. So तो ये देखो 5 by 6 into e raised to power minus t by x exponential e raised to the power any negative value, it will decay. That response will decay with respect to time. It will not grow with respect to time. अगर e का power positive होता तो it will exponential growth will be there. But here e raised to the power minus something, it is exponential decay. ये क्या हो रहा है? Decay हो रहा है. That means it will reach its original steady state. It will reach its original steady state. Okay, मैं बार बार बता रहा हूं कि the see this is capital Y. इसका मतलब क्या है? अनस्टेडी स्टेट वैल्यू माइनस स्टेडी स्टेट वैल्यू. मैं स्मॉल y इसको रिप्रेजेंट करता हूँ. स्टेडी स्टेट है ना? ठीक है. तो ऑलवेज इट इज जब भी मैं इसको कहता हूं कि ये क्या होता है हमारा yt जो होता है, इट इज एक्चुअली स्मॉल y and a process value which is function of time itself minus steady state value. It is also a function of time. Is this okay? Are you getting my point? Just a minute. From our institute. Just yeah. Hello. हाँ. So ये बातें क्लियर है हमारी कि yt क्या है? इट इज अ डेविएशन वेरिएबल. ओके. तो ये हमारा जो है, ये हमारा एक्चुअल वैल्यू रहेगा. ये स्टेडी स्टेट वैल्यू है. ये एक्चुअल वैल्यू रहेगा. जैसे टेम्परेचर है ये 25, स्टेडी स्टेट सपोज मान लीजिए 20. ये चीजें क्लियर है. ठीक है. Now let's move on our picture now. So we are at here. Impulse clear हो गया? Impulse. Now we are moving towards next.
Hello, sir.
हाँ बोलो.
Sir, here xt is equal to a, no? So Laplace of xt will be a by s, no? But here we have taken a.
No, that's the property of this. See, what is the impulse? Impulse. This is the property of. This is just like it is a property of Laplace. When it is an impulse, see step. This is not the step change. If you observe the nature of this, okay, impulse change, it will reach up to some point and then again sudden it will return back to its original value. This is the nature of impulse. But what was the step? Step was like it was here only. It will remain for this change. It is not returning back. It is not coming back. Are you getting my point? So this is the property of Laplace. This is the property of Laplace. When any magnitude, A is any magnitude, is multiplied by a unit impulse function. Okay, then the Laplace of that input is magnitude itself only.
Okay, sir, got it.
This is actually B tends to 0 means that thickness of this rectangle is very, very small. It is, we are just approximating it as a rectangle, but it is not a ideal case. Okay, this is the property of, remember one thing, अगर impulse forcing function है तो magnitude itself the Laplace transform. Remember one thing, this is the property, है ना? जैसे लिमिट की प्रॉपर्टीज होती है, डेरिवेटिव्स की प्रॉपर्टीज होती है, likewise. Okay, we are not going to derive it. Just remember this thing. Fine.
Yes, sir.
Okay. So we will move on the next one. A ramp or linear function. As I had explained that ramp or linear function is something like that. The temperature is changing 12 degrees centigrade per minute type of thing. Flow rate is changing by per minute. Okay. So whenever the per minute will be there, that will be the flow rate per minute. Concentration per minute is changing. Okay, so likewise, that cases, if any input is subjected in such type of particular changes, then we call as a linear function or the ramp function. It is a inclined line. Are you getting my point? It will be the inclined line. ठीक है? So that time my ft function, ft और xt, okay, यहाँ मैं यहाँ xt लिया है, यहाँ ft लिया है, हम इसको और कर सकते और ठीक है? The ft that xt is 0. There is no change at a steady state before time t is equal to 0. But as soon as time t is equal to 0, the temperature starts increasing linearly. Temperature starts linearly. So xt is equal to y is equal to mx का function जो होता है ना? Y is equal to mx. This is the slope. Okay, so इसका एक्सेस क्या आएगा? m by s square. Okay, so this will be the slope. M is slope. M is slope. Okay, so we can rewrite it as again like this. Means ये इक्वेशन हमारा ये है, ओके, इसका स्लोप है m. If slope is m, this will be the xt, this is the time. Okay, what will be the equation of xt? Y is equal to mx plus c, but c is not there, so it is the slope mt, है ना? Y is equal to mx. Likewise, okay, so what will be its Laplace? It will be m by s square. M by s square. Are you getting my point? Axis is equal to m by s square. Okay, okay, likewise. Fine. Okay, now take an example of this thing for the ramp. A thermometer is observed to exhibit the first order dynamics is having time constant of 8 seconds, and it is placed in a bath. After the thermometer reaches steady state temperature of 30 degree with the bath, the temperature of the bath is linearly increased with time at rate 3 degrees centigrade per minute. Sketch the response of the thermometer, determine dynamic error and time lag for the system. Okay, these are the some properties of, just like first order system का हमने step change में जो properties देखी थी, so some properties we can define over here called as dynamic error या time lag. Okay, we will discuss that dynamic error and time lag with this particular example. See here. So the thermometer, I know this is the first order system. So equation 1 is nothing but the transfer function of the thermometer. Ys by xs is equal to 1 upon tau s plus 1. And the change is ramp change linearly increase with, so xt is equal to mt, xs is equal to m by square. Substitute m by square into the 1. This will be like this, m by s square, and again I am taking tau out of this bracket. So m by tau upon s square, s plus 1 upon tau will be the equation number 2. So using partial fraction, since this equation number 2 is not the standard format, so that we can utilize inverse Laplace to make it convenient for the inverse Laplace transform. For that purpose, I will take partial fraction. It will be in this fashion. So ultimately, A is mt, B is minus m tau, not mt, and C is equal to m will be the values we can assign by using partial fraction. So the equation 2 in the separate format will be like this as a equation number 3. And if you observe that s plus 1 upon tau, easily we can take the inverse Laplace 1 upon s, we can take easily Laplace 1 upon s square, we can take easily Laplace, inverse Laplace. So taking inverse Laplace of equation number 3 on both sides, so yt is equal to m tau e raised to power minus t by tau minus m tau plus mt will be the our inverse Laplace equation. Equation number 4 is very much important because the equation number 4, and at ultimate steady state, when t tends to infinity, yt is equal to, this is very much important, yt is equal to mt minus tau. T minus tau. See, the steps are same. The only thing is that the format of excess which we are introducing into the system, it is different. And so that because of that, the response equations which we are getting, it is different. Okay, is this okay? Any question on this? What is ultimate steady state? Ultimate steady state is that when t tends to infinity, by substituting in the equation number 4, and it is we can this is the situation whenever the change introduced enter into the system. So the ultimate change, it may be a different, it may be the same as that of the steady state, the ultimate steady state. Okay, we will discuss that thing. The permanent change may be possible. Permanent change may be possible. क्योंकि देखिए रैप में, are you getting my point? Am I audible? Am I audible? देखिए स्टेप चेंज में क्या होता है कि 25 to 30 अगर मेरा टेम्परेचर बढ़ता है तो 25 पे वापस आएगा क्या मेरा सिस्टम स्टेप चेंज में? 25 पे वापस आएगा क्या? नो। तो अल्टीमेट चेंज हो गया फिर उसका 25 to 30. तो 5 का मैग्नीट्यूड ऑलवेज विल बी देयर. इट विल नॉट रिटर्न टू बैक टू इट्स 25 बिकॉज माय सिस्टम इज नॉट लाइक दैट. मुझे चाहिए 30 डिग्री, मुझे 25 नहीं चाहिए. तो बगैर वो इनपुट चेंज है, एक चेंज आ रहा है उसमें, है ना. बट इम्पल्स में क्या हो रहा है? इम्पल्स में क्या है कि भाई कुछ एक्सटर्नल वाटर में उसमें ऐड कर रहा हूं लिक्विड लेवल टैंक में, but ultimately it will come to back to its original state. Just imagine the things. इसलिए there is a decay. If you observe the graph, it is a decay in the impulse. रैंप में क्या हो रहा है? रैंप में तो बढ़ते जा रहा है with the slope of xt is equal to mt. तो t तो इंफिनिटी हो सकता है, t इंफिनिटी हो सकता है ना. There is no restriction for t. टेम्परेचर बढ़ते जा रहा है, बढ़ते जा रहा है, बढ़ते जा रहा है, बढ़ते जा रहा है, जैसे बॉम्ब में होता है, बॉम्ब एक्सप्लोजन में होता है, टेम्परेचर बढ़ते जाता है. वैसे अगर टैंक में अगर इनलेट फ्लो रेट बढ़ते जा रहा है विथ रिस्पेक्ट टू टाइम, तो वो भी एक लीनियर चेंज है. व्हाट विल हैपन? ओवरफ्लो में टेक प्लेस. या फिर कम होते जा रहा है तो ड्राई, दैट टैंक विल गो ड्राई. तो देयर विल बी नो चांसेस ऑफ रिटर्निंग बैक टू इट्स ओरिजिनल स्टेट. तो ये क्या होता है? अल्टीमेट चेंज. तो अल्टीमेट स्टेडी स्टेट व्हाट विल हैपन इफ टी टेंड्स टू इंफिनिटी, इसको हम कहते हैं अल्टीमेट स्टेडी स्टेट. आर यू गेटिंग माय पॉइंट? ओके. सो द डायनामिक एरर क्या होता है? डायनामिक एरर ये होता है कि it is a difference. Dynamic error, we can say that it is a formula xt minus yt. The value of xt and value of yt at steady state. It is a difference at steady state. What was the value of xt? xt क्या है? xt is empty. xt is empty. What is yt at steady state? M t minus tau. New steady state. M t minus tau. So this will be m tau. This will be m tau. The value of xt, the difference between value of xt and value of yt at steady state, and this is called as dynamic error. That dynamic error will be always there. और time lag क्या है? Time lag is nothing but it is defined as the time taken by the response to reach the value of the input. To reach the value of the input. Okay, इसका ग्राफ है कि हमारे पास नहीं है. To reach the value of the input, that is nothing but our time xt by m. So we can say that it is a nothing but tau. That is the our time constant. Okay, it is defined as the time required to reach the input change to the output. ठीक है. तो इसका एक सिंपल ग्राफ है. लेट मी शो यू द ग्राफ. एक सिंपल ग्राफ by which we can you will get the idea कि what is that. So graph for this is we can say that color लेता हूँ कुछ और the graph is okay. So this is xt and this is yt. If we say xt and yt for the RAM. Okay. So here, if so, let me tell you. This is xt graph, huh? This is xt. क्या होगा भाई? This is xt. If you observe, okay, this is xt. In this case, xt is mt and yt is at steady state mt minus tau. So ultimately, this graph represent that. This graph represent that कि this xt when enter into the system, okay, यहाँ enter हो चुका है, but it will take some time to reach at yt, okay, and this time, that particular value, the time, this time is nothing but my tau. This time is tau. Means ये value yt में कब मिलेगी? After that time. जैसे पाइप है मेरा, एक पाइप है, ओके, यहाँ एक टेम्परेचर चेंज हुआ है, तो सेम टेम्परेचर 25 हुआ है फ्रॉम 22 टू 25. तो यहाँ जब 25 आने के लिए कितना टाइम लगेगा? द टाइम ट्रेवल द डिस्टेंस ट्रेवल एंड टू ट्रेवल दिस चेंज is of tau time. It will reach at the exit in tau time. This is called as time lag. This is called as time lag. Fine. So my question is कि भाई अब रिस्पॉन्स करना है, स्केच करना है. Tau is 8 second. Slope is how the temperature is changing linearly. It is 3 degree centigrade per minute के लिए change होते जा रहा है. We will convert into the second. Since that tau is second, either it convert into the minute or either it convert into the second. So steady state क्या है? Xs is equal to ys. Initially steady state क्या था? It was यहाँ 32 है. Okay, one more was here 30. ठीक है, तो here should be 30. So xs is equal to ys is equal to 30. So I have the value of m, I have the value of tau. Substitute the different value of time. Identify y. Okay, तो आपको वही चार्ट बनाना है. 0, 1, 2, 3, 4 and y की वैल्यू and y की वैल्यू. What is dynamic error? Dynamic error is m tau. Dynamic error is m tau. M is 0.05 into t. What is time lag? 8 seconds will be the time lag. After 8 seconds, the RAM change you will observe into the output. This is the property. Don't go in that. The dynamic error and the time lag. Okay. So this type of questions I will ask into the examination. Okay. Today we will stop here because the sinusoidal one which we have left, it need a little discussion, and 10 minutes is not sufficient. Okay. So any question regarding this? In the next lecture, we will go for sinusoidal forcing function. Any question regarding this?
Sir, I didn't understand the part of like ultimate steady state. I got the concept, but how did that expression arrive for yt at ultimate steady state?
That equation 4, na?
Yes, sir. After like from equation 4 to the next equation.
See here, that one. Okay. I'm just showing you the. See here, the equation is ultimately yt is equal to m. If I'm replacing it, okay, I'm just rewriting it again. It is like that: tau minus m tau plus mt. Okay, this is my equation. Okay, and I'm just rewriting it in the fashion like taking m common, m t minus tau will be there plus m tau e raised to the power minus t by tau. Okay, so when we say at time t tends to infinity, so exponential term will vanish. Whatever the variable will be there with respect to time. At time t tends to infinity, the exponential term will decay, so it will vanish. It will vanish, and only remaining will be t is too much large, therefore it will remain as it is. Are you getting my point? Mathematically, got it?
Yes, I got confused about the limit, sir. Yeah, now I got it, sir.
Yeah. Okay, fine. Okay. Any other question? Any other question? Okay, so we will stop here today, and the sinusoidal we will start from the next lecture. Fine.